All right, so this is Unit 9, Statistics and Probability. There we go. We got some basic skills that you have to know about. You have to know how to convert things between fractions and decimals and percentages. Those three things are very important for this one. If you don't know how to do that, you're going to have a lot of trouble with this unit. So a hundredths chart can help if you're really not sure what to do. So the shaded part of this grid can be described in three ways, if you can see that shaded part there. There's 16 blocks shaded out of 100. This is a hundreds chart, so there are 100 blocks there. So you can write it as a fraction, 16 over 100. And if we simplify that, what would that be equal to? 16 over 100. Both are divisible by 4.
4 over 25?
Yeah, 4 over 25. That would be the simplified version of it, right? So 16 100ths is the same as 4 25ths. We can also write it as a decimal, this grid right here, as 0.16. And as a percent, remember, cent has to do with the number 100. So percent, 16 per 100, 16%. That's what that means. Or you could even write it as 16 out of 100. That was a fourth way that someone came up with last year that I added to my notes, but I haven't obviously fixed it. So I thought that was pretty clever of them. All right, so we're going to convert fractions to percents. So fractions to decimals and then decimals to percents. And this is kind of the longest process. So
a lot of this should be review.
If it is review. This is grade 5 or 6?
No, percents we don't hit till 7.
Oh, interesting. I thought percents was 6.
It might be a little 6, but either way. So just if some of you've never seen this before, know that you should pay super close attention.
Yeah. Okay, so 3/4, we just divide the top by the bottom. Then you get 0.75. And we times by 100, a cent, right, percent, to get 75%. So if you got 3 questions out of 4 right on a math test, you got 75% on that math test. So the simplest way is top divided by bottom times 100. That's it. So 3/5 is 3 divided by 5 times 100 is 60%. 3 divided by 5 is 0.6 times 100, 60. So fractions to decimals, top divided by bottom. Oh yeah, that's the, yeah, that's me trying to make up because I did that a little bit all in one step here when I had explained it in 2 steps before. Okay. So if you're just going fractions to decimal, you're just dividing top by bottom. And decimal to percent, you're just timesing by 100. That's it. So together, top divided by bottom times 100. So converting percents to decimals, this is actually the easiest. All you're doing is moving the decimal spot 2 spots over to the left. So we're dividing by 100, and you get like percent. And you get 67% divided by 100 is 0.67. 45% divided by 100 is 0.45. And then we're going to convert percents to fractions. So if we've got 12%, 12 per 100, 12 over 100, and then we simplify. So all you're doing is you're shoving whatever number you have with the percent sign over 100. That's it. So if you have something that's 325%, you're putting that 325 over 100. If you simplify that out or you turn it into a decimal, you get 3.25. It'd be over 1. 12 100ths in this case does simplify down to 3/25. Both 12 and 100 are divisible by 4. Next year, if you stay in pre-calculus and foundations of math, there's going to be a lot of this stuff in there where you have to figure out common factors of 12 and 100. And there's some nice tricks on how to do that that you'll learn from Ms. Windrum. All right, so this was an assignment that I'm not giving you because I have given a different one. And it's going to be up online right after the class. I just haven't posted it yet. So there's some more examples for you. Theoretical probability. So this is the probability of an event occurring. It's equal to the number of desired outcomes divided by the number of possible outcomes. And by desired outcomes, we're not talking about things that we want to happen. We're talking about things that we're wondering about happening. It's more than, I never like that word desired for this. I'm curious about this. So you put that on top out of the total number of outcomes. So we say the probability of this event happening is this number over that number, or this number out of that number. So if we roll a die, and what is the chance of a 4 being drawn? We want a 4. Well, the desired outcomes, there is only one desired outcome that we want. It's a 4. There's only one 4. So there's only one outcome that we're interested in. And the number of possible outcomes on a regular die, I should say a D6 for all of my D&D kids, sorry. There you go, a D6 die. Means there's 6 sides on this die. There's 6 possible outcomes, a 1, 2, 3, 4, or 5, or 6. So 1 out of 6. And only one of them is labeled with a 4. So the probability is 1/6 of rolling a 4 on a die. Really, the probability of rolling anything on a 6-sided die is 1/6. Any one side, that is. So what's the probability of rolling an even number? Well, even sides, there's 2, 4, and 6. So 3 of desired outcomes. And all sides are 1, 2, 3, 4, 5, 6, 6 possible outcomes. Well, 3 over 6 can be reduced. They're simplified down to 1/2, which means that there is at 1/2, there's the chance of you rolling an even number is half, 1/2, or it's 50%, or it's 0.5. Any of those terminology will work just fine for this unit. So here's an assignment that we're once again not going to do because I've got something else up online for you in just a moment. Experimental probability. This is one that we do in class. And so this is last year's version. I'm just going to briefly go through it instead of running you through experimental probability. You've been doing experimental and theoretical probability for a couple of years already. So remember, theoretical probability is talking about the number, what's the likelihood of what you want happening based on how many instances is there of what you want over how many total outcomes there are, and figuring out what that theoretical probability is. But we all know, because life is fairly random, that that doesn't always necessarily happen. And experimental probability is the number of times the desired outcome actually happens divided by the number of times the experiment is conducted. So in this case, we did it 25 times. I'm just gonna make that 25. There we go, that's neater. A die is rolled 25 times with these results, and this is what we did last year. There were 5 1s rolled, 4 2s, 5 3s, 4 4s, convenient, 4 5s, and 3 6s. So you can tell the percentages are a little off, as to, you know, all of them should be exactly the same, right? Because they've got the exact same probability theoretically of rolling, but they didn't. So to roll a 1, it ended up being 5/25, or 1/5 of all rolls were 1s. 4/25 of all rolls were 2s. 1/5 were 3s. 4/5 were 4s, and 4/5 were 5s, and only 4/25 were 4s, 4/25 were 5s, and 3/25 were 6. So That's a 20% chance for 1s and 3s, a 16% chance for 2s, 4s, and 5s, and a 12% chance for 6 in that case is the math there, which has been done very badly here. Sorry. It looks like those two are connected and they're not. Should be like that. Took me a minute to figure out what I had done there. So I'm not going to assign this either, so you don't have to do this one. This is the meat of the unit right here, not the unit, the section here. This is the rest of it was prerequisite learning that you needed to know. Now this is what you're expected to also know in grade 9. So if any of that stuff was new, you've got a little bit of catch up to do, so you need to make sure that you work on that practice assignment really well. You can go to Khan Academy and look up some more help on statistical, theoretical probability or experimental probability. You can also do the assignments in here in this slideshow, and I'll correct them as well if you send them back to me. So we can use probability to help us make decisions either based on theoretical probability, which is what should happen, right? Or experimental probability, what has happened in the past. But sometimes the decisions we make are influenced by our state of mind or by gut feeling, and this is what is called subjective judgment, what we feel should happen. And let's explain what those things are. So these are some examples of what they are. Explain how each decision is based on theoretical probability, experimental probability, or subjective judgment. So it is Ozma's experience that 4 to 5 times the prize in a cereal box is found at the bottom, although they don't have prizes in cereal boxes anymore. So I'm sorry, this is old. Have you ever had a prize in a cereal box?
Oh yeah, as a kid, but not recently.
Actually, yeah, I actually have.
Have you? Okay, man. Yeah. It was a thing that was like in every box, almost every box of cereal. I mean, sometimes you wouldn't buy a box of cereal if it didn't have a toy, but that was kind of funny.
Yeah, I actually have honeycomb socks.
Oh, nice, honeycomb socks. That's cool. Yeah, the lamer ones were when you had to cut off a piece of the box and mail it in, and then they would mail you your prize. The best were like when you could dig in through the cereal and get your prize out, and it was all covered in cereal dust, and you'd unwrap it. They were usually some stupid cards. At any rate, they were heavier than the cereal, and oftentimes you would find them at the bottom of the bag. So Ozma is going to try and open her box at the bottom of the box, right? To get to the prize immediately. So from her experience, 4 to 5 times, she opens the prize at the bottom. This is based on experimental probability. 4 times over the past 5 boxes of cereals, she has dug in there right to the bottom to get that prize, which is kind of fun. All right, 2 friends are rolling a die. Out of 8 rolls, 4 came up 7 times. That's kind of crazy, hey? Ameth predicted that the next roll will likely not be a 4 because each number has an equal chance of being rolled. Maria decides the die is unfair since 7 out of 8 rolls revealed a 4. So what is Ameth saying? What's he using with his prediction that 4 is likely not going to be the next roll?
Well, basically that every single number should have got rolled at least once. But
yeah. So is that theoretical, experimental, or subjective judgment?
Theoretical?
Yeah, he's using the theoretical. Yeah. Wow, that's really weird that 4 came up that often. I probably won't come up again because that's theoretically odd, right? What about Maria? She just decides it's unfair since 7's being rolled so often, or 4 is being rolled so often. Is that theoretical, experimental, or subjective judgment?
I'd say subjective.
Mm-hmm. Yep. That's the thing you'll notice about subjective judgment. all of these things have certain hints. If it's based on something someone has done multiple times, that's experimental. If it's based on, wow, that's super unlikely, or that seems like that's not likely, or that would be probably what would happen, that's theoretical.
Experimental. Oh,
Right? If it's not based on what has happened, but it's based on what you think should happen. But subjective judgment is different. It's based on feeling, and it usually doesn't have anything to do with the stats itself necessarily. So, and in this case, speaking as someone who plays Dungeons and Dragons, I would worry that that D6 that she's rolling is probably not weighted correctly. I would be all over that subjective judgment too. I get it. Oh, I bet you
that would be scary if you just kept on rolling it.
Yeah.
A 4.
Well, it would mean that the dice is imbalanced if it were to continue to happen. If you were to do 200 rolls and a 4 came up like 70% of the time, 80% of the time, you'd probably want to put that dice in a glass of salt water and just to see what actually comes up, to test if it's actually accidentally rigged or not. Because that does happen. You do get imbalanced dice sometimes. All right. So sometimes we take certain things for granted when we make decisions, and these are assumptions. So in past baseball games, Alice made 2 hits for every 5 times she went up to bat. 2 desired outcomes, the hits, for every 5 times total that she went up to bat. So in the next game, suppose Alex goes up to bat. What is the probability that she will get a hit? Well, 2 is the desired outcome divided by 5, which is the total times. So, which is equal to, we're working backwards here. It's really weird that I did it that way. Bizarre. I would just go 2 divided by 5 times 100, and you'd get 40%. 2/5 is 40%, or 0.4. Any of those answers would be correct. All of these answers actually are correct. I wouldn't mark any of them wrong. This 4 out of 100, I would question why you would leave it that way if you gave me that one, because you know better than to leave things in an unreduced fraction form. So some assumptions that are being made. What situations would change the probability of Alice making a hit? If she doesn't go to the game, she's not going to make any hits, right? What if she broke her ankle mid-game? That's going to change her score. What if there's a really nice pitcher who's lobbing things right at her? She'll hit more often. So there are some assumptions that we're making, and this is the hard one. I find my classes struggle with these assumptions. And so don't overthink this. All it is if you changed something, would the stat change? Okay, give me an example of what that is that would change the stat. And so think a little bit outside of math here. This is, honestly, it's a very strange unit because it's got a lot to do with English rather than strict math. Does that make sense? It's a little weird. All right. So Ms. Lamb notices that usually 3 students of 24 leave the classroom every period to use the bathroom. Oh yeah, I came up with this one because I had one class that was just like, they must have had incontinence issues. What is the probability that someone will use the bathroom this period? Well, 3 divided by 24. This is based on experimental probability because that's what I have noticed, not what not what theoretically should occur, which is equal to 1/8. 1 divided by 8 is 0.125, and times 100 is 12.5%. There's a 12.5% chance that someone will use the bathroom this period. And what assumptions am I making? What could change that number? Ms. Lamb, the assumption is that Ms. Lamb will continue to let people use the bathroom. That, once again, this was a jab at that particular class. Because I wasn't going to continue to let them use the bathroom because it was a little insane. Keeping the tap on. Maybe if I leave the tap on and let the water run to clean fish tanks or whatever, that sound of water might influence more people to use the bathroom. Maybe students all came with tea that day, and tea will make you use the bathroom. Or maybe people are cold. Also, if you're cold and you want to warm up, a good way is to use the bathroom. It's weird. Your body needs to work, like spend energy heating the water in your bladder. And so if you get rid of that water in your bladder, your body doesn't need to expend the energy heating it, and it just heats you up more. So there's some handy tips there. And that's basically it for this particular section. I didn't realize that was all I had. So I'm going to stop the recording. Thanks for joining us.